I want to slowly lead you to properties, categorical properties of the representation theory of vertex algebras, and I feel it's a good idea to first present a few invariants. For example, the fusion rule is clearly an invariant, right? It's the number of intertwining operators. These are the ones that will eventually define our tensor product. There are some well-known miracles, and one well-known miracle is that you can compute this fusion rule in a very different way, and that's a very pleasant computation, so this will be the rest of today. And another thing I want to introduce is I want to compute, and the computation is not long, but it's quite technical. So I'll give you the essential steps to see this commutativity, the skew symmetry isomorphism, fairly explicitly in the free boson case. Okay, which probably will be the first thing tomorrow. And once I have done that, I will do an excursion on tensor categories. And then state you the main theorem of E.G. Huang, and then tell you more. Okay, now before I started, I was asked to give a comment. So if we have an intertwining operator of type of 3 modules, and all of them simple and Z-graded, then we had this duality statement, and a priori arbitrary powers of a Z can appear. But in this statement, or it was a Z2.
What do you mean by Z-graded? Does it mean L0 has only integer eigenvalues?
Z-graded means by a coset of the integers. By a single coset via L0 eigen.
So I think that should be
graded by H1 plus Z, H2 plus Z, H3 plus Z. So by 3 chosen cosets, there exist 3, let's call that conformal weights of the top level. 3 such weights, H1, H3, and H1, 2, 3. And then the statement is that it's everything we had is the Z2 powers that appear are of the type, and I hope I get the signs correct. It definitely only depends on the sum H1 and H2 minus H3. And then we just get power series in Z2. Right? So this means the thing I wanted to point out, or I was asked to point out, I was forced to point out, is that not any arbitrary complex number appears here, but it's completely determined by conformal weight. And I should also point out is there will eventually be a certain condition that ensures that fusion products are finite, in the sense that the spaces of these the dimension of these vector spaces are finite dimensional. That only holds if certain good condition holds. So beyond that, anything can happen. It's mostly unknown. But and then the possible exponents are completely determined of Z2 are completely determined by the conformal weights of the involved modules via a formula like this. Okay, so this is something a comment on this morning.
Can you state this as a statement for some time? What was the statement?
The statement, we had this duality statement in the definition of then The problem is writing it always takes quite a few minutes. This is the statement I explained in words.
Statements under some hypotheses.
Sure. Under this hypothesis here.
Under some hypotheses, any intertwiner has this form as the statement.
Yeah, so if you have an intertwining operator between simple modules that are z-graded in the sense that the conformal weight is just going over a single coset of the integers, then the form of the power series is completely determined by these weights, and that's it. So in particular, it doesn't look as horrible as previously announced.
But moreover, this is actually the general case.
That's actually a
Simple modules are graded like this.
And now I put here. So this can be happen slightly more general. So for example, what sometimes happens is that you have a 1/2 here, then you have to allow for all these halves as well. So that makes it a little bit, but you can of course rectify it by simply putting the 1/2 here, and you're good. Yeah, but I think that's all that can happen. So I've never seen anything beyond. Now, okay, let me go on. So one defines what's called the graded character of a Fock module, and of course I could define this for a general module. And I like to define it as a function in 3 variables. The y just goes along, it's just multiplied by y, and don't attach much meaning to it. It's just for convenience in a few minutes. Then the trace over this module as a vector space. And this one is naturally graded by the Virasoro, by conformal weight. Now the convention is that one adds a -1/24 here. The 1 is reflected that the central charge of this Heisenberg algebra is 1. In general, you put the central charge here. Then it's also naturally graded by this x0, the 0 mode of the Heisenberg algebra. And now let's think about it. What is this vector space? Well, as a vector space, it's just polynomials in the negative modes. The negative mode x negative n has eigenvalue L0 x to the n. So this means I have any monomial in x minus 1, any monomial in x minus 2, etc. Any product of those, this gives us a basis. So if you think about it, the character should be something like this expression, I mean 1 over this expression, is definitely the graded character of polynomials in infinitely many variables, if I give them degree 1, 2, etc. And this is well known to be the Dedekind eta function, except of this thing. But this, if I put this thing here in the denominator, I get precisely the Dedekind eta function. That's good. And now, what else? x0 acts as on the highest weight by multiplication with lambda and commutes with everything. So this means this x. So first of all, the y I just had as a prefactor. The x0 just gives me a z to the lambda, because x0 acts just as multiplication by lambda on the whole module. And now all I need to know is how does L naught act on the top level of the module. And it turns out it acts by lambda squared over 2, which is a good exercise to compute. It's not a difficult one. Okay, yeah, anyway. So it turns out one introduces this graded character, and well, it is this one. So, and let me write it once more. It's y z to the lambda q to the lambda squared over 2 divided by Dedekind's eta function. Right? Those of you who know about modular functions, they have definitely heard Dedekind's eta function. It is often also called the partition function because its expansion coefficients count the number of partitions of a given integer into integers. So it appears from there.
Can you maybe write this down? I should know this. I realize I should know this. But
We have
in this case, we have only one x, right? So we have x0, x1, etc.
yeah. So
And,
so
oh yeah, see. We say in degree n are monomials.
yeah, yes. Let's see. Right, you do the counting, right? An arbitrary.
Anyway, no, okay. I take my question back. I think I can figure it out.
Yeah, but it's a good exercise again. Many good exercises, right? It's yeah. So this thing here in the denominator is the Dedekind eta function. Okay, now and of course here in order to make here this 1 over 1 minus q to the n is of course interpreted as the geometric series. So I'm here always requiring that q has absolute value less than 1. Right? And then this makes sense. Okay, now what do? We set y to be e to the 2 pi I something, z to be e to the 2 pi I something else. What did I call it? U. Q to be e to the 2 pi I. Here we take it tau, because what do we want? If we want q to have absolute value less than 1, then we want tau to be in the upper half of the complex plane, right?
What is q to the lambda squared over 2 supposed to mean?
It comes from this L naught.
I understand how you got it, but now if you're taking q to be an actual complex number, what do you mean by q to the lambda squared over 2?
I mean this.
But then, so what is log q?
Yeah, right. I actually want to do one thing now. I want to restrict to lambda real. Okay. Yeah, I wanted to restrict to lambda real now. And so let's see. So this means we have here this 3-variable function, and now I want to define an operation on these 3 variables. So an operation I call S, which maps this tuple, this triple. It maps t to t minus u squared divided by 2 tau. U gets divided by tau, and tau gets inverted and multiplied by -1. And t doesn't do anything, and t and u, and translates tau by 1. So then why do I do this? I think anybody, why do I do this? Some of you know, so let's check a few relations. So for example, what does S squared do? Well, I take my triple here under S. That gets mapped to what I just wrote down. And then I apply another times S to the answer. So then the new tau gets replaced by by the new t gets subtracted this one squared divided by 2 times this one. And what does that give us? It gives us exactly the summand again, but with an opposite sign, so that we get just a t back. What happens to u over tau? It gets divided by this expression, so the tau's cancel, but we still have the minus sign, and negative 1 over negative tau, 1 over minus 1 over tau gets replaced by minus 1 at this expression divided by, and then the 1 over tau in the denominator, so we just get 1 over tau, we just get tau back. So we see, I'm sorry, of course here was a tau too much. So we see, s squared is almost the identity, it just multiplies u by -1, in particular s to the 4 is the identity. And similarly, one can check, it's just a little bit longer, that st cubed has the exact same property. And so we see, this transformation, the group generated by these transformations, I mean by st and t inverse, is the group that satisfies these relations. But what is the group that satisfies these relations? It's exactly SL2Z. All right, that's the group generated by 2 elements subject to the relation that s to the 4 is equal to st to the 6 is equal to 1. And usually you think about the S in terms of 2 by 2 matrices with integer coefficients, and then, for example, the action of SL2Z on this tau is exactly given by Möbius transformations. So that means, in particular, the matrix A, B, C, D acts on tau via Möbius transformation. Okay, so this means if I do this transformation of variables, it induces an action of SL2Z on these characters of Fock modules. And now let's see what is the answer. How can I express these transformations? So the T transformation just maps, you see it doesn't do anything on the T and U, so it doesn't do anything on the Y and the Z, and it replaces tau by tau plus 1. So this means we get here an e to the pi I lambda squared, and then the eta function, look at it, if I replace tau by tau plus 1, Q doesn't get changed, so this whole product stays the same, and here I get a 24th root of unity. All right, so that means the whole T transformation just gives me this e to the pi I lambda squared and then an additional e to the minus pi I over 24 over 12. Okay, so the interesting thing is to check the S transformation. And so what I define is now, let me set S lambda comma mu to be e to the negative 2 pi I lambda times mu. And now I do a Gaussian integral, so I take the integral over the real line. This, let's call it S kernel S lambda comma mu, multiplied by the character of the Fock module, and then we integrate over the variable mu. So let's write it down what it is. Let's take out what is independent of mu. The eta function doesn't depend on it. And so we see this becomes, but we have here the character, we have our e to the pi I mu squared, pi I tau mu squared. We have this term, e to the 2 pi I mu. U times mu. And then what else do we have? We have the term here that comes from the S kernel. Okay. And now we know that this is in the upper half plane, so the imaginary part of tau is positive, I times it. So that means the real part. So this means it's this term is of type e to the minus a square of a real number plus something imaginary. So what can I do is I can apply a Gaussian integral. And if I do this, what do I get? Let me first write down the integral, the answer, and then remind you what I mean. So as an answer, you get this expression, and now I claim this is exactly the character of pi lambda, but instead of the variables y, z, and q, I insert their S transformed variables. So I replace t by t minus u squared over tau, and indeed we see here t minus 2u squared over tau, t minus u squared over 2 tau, and you see that term exactly appears here. All right. I replace my u by u over tau, and indeed we have here a term minus 2 pi plus 2 pi I lambda u over tau, exactly as desired. And then I replace tau by minus 1 over tau, and indeed we have here a term e to the pi I times minus 1 divided by tau times lambda squared. Right? Exactly the terms appearing here if I replace y by the t by this one, etc. Okay? So this, if one stares at this, one sees this. And how do you come up with this equality? Well, this is a Gaussian integral. So let me recall this. Let me recall a Gaussian integral, and then that answers your question. So we have an integral over the real numbers of type e to the negative a mu plus b squared d mu. And what do we get here? We get a square root of pi divided by a. Oh, well, I could have written that there. As long as this converges, as long as the real part of a is positive. If we look at this clearly, we can write this, complete this to a square, right? We just have to do our, you just have to rewrite this. If you complete the square, you get this additional term here. So that comes from this term comes from nothing but completing the square here. But then you have your Gaussian integral, and the Gaussian integral gives you a pi over square root of pi over a. Well, a will be, because we have the pi in here, be pi times something. So that will cancel, but it will be the a will be square root of minus I tau times pi. And that's where it comes from, and that's perfect because the S transformation eta of minus 1 over tau is exactly this thing. Okay, so nice computation, right? I hope you find that. Okay, so why do I do this? Because now I maybe misdefine this, but this is what Verlinde initially meant with Verlinde's formula. So I hope for him that he didn't call it like this. That would be, but you should never call it after yourself. So in the 80s, end of the 80s, there were two really good papers, one by Verlinde and then another one by Moore and Seiberg. The Verlinde was first, and Moore and Seiberg were more detailed. And it was about the fusion rules of rational conformal field theory, and then Moore and Seiberg much more about the relation to modular tensor categories. They didn't call it that time modular tensor categories, but because it didn't exist. But from physics principles, one expects that torus one-point functions, so characters are special cases of torus one-point functions of a conformal field theory, to have good modular properties. Well, of course, they are functions on the torus. But the interesting thing is that not only one expects this, but one also expects that the modular transformation reflects the fusion rules in some way. That means that there exists the modular S transformation gives you immediately on the nose a formula for the dimension of conformal blocks. I mean of three-point correlation functions, the ones we wrote down here. It took a very long time, until 2005, until E.G. Huang proved this in the setting of rational vertex algebras. There were more geometric proofs where one translated the statement in a different language. Anyway, that's the motivation. And now, I will say much more tomorrow on categorical things, including Verlinde's formula. At the moment, I only did this in order to motivate this definition. So I define the Verlinde product. So it's a product on the space of characters. Let's call it a product with a V. V not standing for VOA, but for Verlinde. And it's defined as the integral over the Verlinde fusion rules so that's this thing here, where the Verlinde fusion rule is defined to be an integral of our S kernels. Okay. Now, well, I can define whatever I want, right? But
actually, you defined already n lambda mu, so is it the same as?
Yeah. So let's give it the old one. We think about now having an index F for fusion or V for VOA, and this one we give now an index for V for Verlinde. So now confusion can arise. Let me just give it in Ver for Verlinde here, okay? So that we and then the old one can stay as it is for the moment. And they are the same, yes.
Is that S0 row under the denominator?
It's exactly this one.
Okay, so we take one of them to be 0.
You take lambda to be 0 then, and of course if S0 row is just 1.
Okay,
so I could just have left it out.
Okay.
Yeah. I could have, here in this formula, there was no need for me to write it here. But you'll understand why I wrote it later tomorrow, right? I just wrote it because that's the natural formula. And
So I guess the star belongs to the S mu rho.
and the star is just complex conjugation. So I could equally well have written S minus nu rho, and it gets here a little bit. These pens are so much better than the old ones, but this is giving up now. Do you know whether we can get some for tomorrow?
We will ask again.
Because there aren't any here anymore.
Okay.
It was a little bit annoying writing the last days because they always gave up, and today was super nice. And I think you also noticed, right? It was much clearer, and because that is okay. So yeah, let's compute this. So we can also note.
Sometimes it's also transposed, but you don't mean this, right?
So you can do that in very many different ways. So usually,
I'm sorry, I take it back. It's symmetric anyway.
Yeah. Usually you like to write an inverse here, but and let me maybe quickly tell you in which sense the complex conjugate here is the inverse, so that. I didn't want to write inverse here, but I mean, so let's just remark. Yeah. So let's just look at the integral of S lambda mu S mu nu. So I think about it as a matrix multiplication, just to know it's an integral, right? And on the second one, I put the complex conjugate. Well, what is this? Let's just write it down, right? It's e to the 2 pi I mu lambda minus nu. And that is a delta distribution, right? If you integrate that against the test function, it has exactly this property. And this is also how we want to think about this product. Right? I purposely defined it in this way because we can already write this down. Right? This one is 1, and what is the numerator here? It is e to the 2 pi I rho times lambda plus mu minus nu. So the integral over rho gives us the delta distribution delta lambda plus mu minus nu. And now I integrate over nu, so that means that integral becomes, I integrate, right, and now I integrate over nu, so that integral gives us just pi lambda plus mu. So let me just write it down. So now we compute the integral of n lambda mu nu.
And it's really a verb, the superscript in front of n.
And there's really a ver superscript, absolutely.
And in the definition there should be as well.
In the definition as well, absolutely, yeah. So we compute this Verlinde product. And now we see, this becomes the integral over rho of this integral over nu of, and now we view our character as our test function. So that gives us the delta distribution. I should probably. So we see. So we see the Verlinde fusion coefficient is not exactly the fusion coefficient that I defined.
What are we missing in your formula?
It should be e to 2 pi rho times this bracket.
So thank you. Thank you. I feel the later it gets, the more I forget. So it's good that we are good for today. Yeah. So we think about the fusion rules we computed as defining a fusion product, namely module 1 times module 1, module 2 is equal to the sum over M3, fusion coefficients M1, M2, M3, module number M3. Now we don't have finitely many modules, so we don't like to sum, we replace it by an integral. And that's actually the novel thing about this. It's nothing deep, but we have uncountably infinitely many modules, so instead of a summation we do an integral. Anyway, we compute, I presented many details on the computation of fusion rules of Fock modules, and we observe the very same rule can be computed also via this Verlinde fusion rules. Now, why do I present this? Because this is not a coincidence, but it's only a theorem in vertex algebras that are not covered by this Heisenberg VOA, but it's a very nice thing. So I will start tomorrow by introducing tensor categories. And one very well knows that in a tensor category you also have an S. The S looks like this. So it looks like this, maybe a little bit nicer. But that's how you write S. It's called the Hopfling S. And it turns out in finite tensor categories with braided tensor categories with a non-degeneracy conditions, you automatically have an SL2Z action where the S is related to the Hopfling. It's a normalized version of it. But something that holds beyond all this finite thing is that the categorical Verlinde formula is, for very trivial reasons, always true in such a sense. So that means you have something defined via Hopflings, and it immediately gives you such numbers, and these numbers coincide with the dimension with the tensor product decomposition, the multiplicities that appear there. Anyway, we will do a lot on tensor category basics tomorrow, and then return to VOAs. And right, and before that, I do that, I will. Shall I do that now, or do we want to stop? Do you want to go 5 minutes early or see one more statement?
I want to see more statements.
Is that the only opinion? Okay, the pen is not good. It's probably good. So okay. So somehow today I'm presenting invariance, some quantities that.
This discussion you had for motivation, what did it have to do with this Verlinde problem?
Can you say it again?
You had some long discussion about integrating this S matrix against characters.
Yeah.
And this, I see no resemblance between that and then what it was close to the motivation.
Yeah. So what I have here is I have characters as here functions in Q and Z essentially, and what I do is if I transform these functions in a nice way, I see that this that the transformation, the transformed character is an integral of characters with certain coefficients. That's all I presented, and the corresponding transformation is the S transformation of the modular group. So that's all I did here. And then I used this S transformation to define some numbers, and these numbers gave me.
But you didn't explain what is the relation.
No, I want to do that tomorrow.
And if I may make a this was you added this y into it, which had nothing to do with the y was completely disconnected from the module pi lambda.
Yeah.
But the y is crucial for this because the y gets changed.
Yeah. So
somehow this seems to be very somehow.
So if
bizarre.
it's not bizarre. So if you have a module for a Lie algebra, how do you grade it? Usually you grade it by a maximal abelian subalgebra, right? By Cartan subalgebra. What's the Cartan subalgebra of the Heisenberg algebra? What is a maximal abelian subalgebra? I have L naught, I have X naught, and I have the central element, which acts on everything as 1. Right? So really, what I wrote down is Z to the X naught, Q to the L naught, Y to the central element. So it appears there. It's in fact the naturally graded thing. You can. Could also have completely left it out.
But in other words, when you transform it, it's no longer 1.
Yes, it's still 1. Yeah, it's still 1.
I mean, y got sent to t was sent to t
minus u squared. Yeah, and this minus u squared over tau was exactly cancelled. Yeah, this is now the S transformed character. No,
what I'm saying is the S transformed character no longer has this thing equal to 1. There's this thing equal to whatever corresponds to t minus u squared over 2 tau.
So this, what this is exactly this thing I'm writing down. So I won't tell you something new because we got too many questions. Anyway, and the tilde means, and here y tilde, for example, means e to the 2 pi I, and then the S transformed tau. S transformed t, and similarly, q tilde means e to the 2 pi I, the S transformed tau, etc. This is exactly this one, right? And you see this by comparing here.
Yeah, but what I'm saying is you said the y in front was actually y to the 1.
Yeah, and it's
the 1 was the value of k.
Yeah, and here it's still here it's a y tilde to the 1. The 1 is still there. Here it's still a 1. I don't understand your question. It's still the 1 here. So usually people don't introduce this because this central element is fixed, so it's just a prefactor that goes along for the right. The price that you pay is that you don't get a modular transformation on the nose, but you get a prefactor, which is the standard automorphy factor of Jacobi forms. Of course, perfectly no problem. It's still very nice. It just I wanted to get a nice transformation on the nose, and so that means and I can do so, right? Because I think one should always take the logic. I have a module for some algebra. That algebra has a maximal abelian subalgebra, so I should grade by everything. Well, if one element always acts by the same scalar, then it just goes along for the right as a prefactor. But I think I should introduce it, and you have to admit that this transformation here is nicer than writing a complicated prefactor. So, but it's a good question.
Another question is, in the definition of T, I was a little bit surprised that it acts by the identity on T and U, and only acts on tau.
Yeah. So I think it shouldn't be a surprise that on T T is really everything is quite mild with it. But you have to think about it in terms of Jacobi forms. So you should think about this is of course not a Jacobi form, but it's mainly graded by two things, by Q and Z, by tau and U. And now you want to do a Jacobi transformation. How does the Jacobi act? So you have your modular group acting, and then you have your translation group acting. And what does the translation group do? It maps in general. The Jacobi group is given by Z times Z, and the action is given by tau goes to tau plus an.
Plus 1, right? And then normally there's some action on C cross C also, right? I mean, if I think of it as the torus
Yeah.
with its complex family of complex structures over the upper half plane, it would also act on the torus. That's why I was confused that there was no action of t on the first two variables, t and u.
Yeah. I do understand your the Jacobi group, how does it act? It maps u to a scalar times tau plus another scalar, and it doesn't do anything on tau at the same time, right? So that's what's confusing it. So you have two groups acting: the modular group, which focuses on the modular variable, and the Jacobi group, which is it's the translation group, right? You have your torus, and that's what leaves your, what corresponds to your torus, which is the Jacobi variable.
Maybe it's because we're using different coordinates.
I think that's the confusion, but yeah.
You move the lattice as well.
Yeah, you move the lattice as well, right? It's here we think about this as we have the upper half plane, what tau corresponds to, and then we have a torus parameterized by it's just a C mod Z tau or ZU. Yeah, right. There the confusion comes. Yeah, absolutely. Anyway, okay. So I wanted to I will start with this tomorrow. The main another thing one could now do is we know our intertwining operators relatively well, and at the beginning of this lecture I had here this skew symmetry theorem, how M1, M2, M3 type intertwiner is related to swapping M1 and M2, and it would be nice to compute this isomorphism explicitly. And I will start with a sketch of that computation so that you see how it differs. And why do I do this? Because the thing that we want to remember for tomorrow is this number, and I would like to get something related to this number in the commutativity isomorphism as well, in the skew symmetry. Right? And then I would like to claim that this is I do all this computation with a thing in mind that everything I do is not a coincidence, but it's happening for deep reasons. So if I compute a commutativity isomorphism and it's up to maybe a square root, the same thing as this one, then that's maybe a sign that there is something deep going on, because there is something very deep going on, and that's what we want to talk about tomorrow. Right? The nice interplay between analytic properties of these trace functions, or more generally torus one-point functions, or maybe more generally conformal blocks, and properties that you get from a purely categorical perspective.
Can you say once more what is gained by this computation over there?
By this one?
Yes. You just say at the end result I just replace y by y tilde, q by q tilde.
Yeah.
Blah, blah, blah. What is gained by the fact that I can do this by such an integral? What is
I want to illustrate that the space of characters carries a somehow nice action of the modular group. That's what I did. So this statement, the T transformation on a character is trivial, right? It's very nice. Just multiplying by a phase.
Would you just say I replace y by y tilde, q by q tilde? That would be your action.
Yeah. So I do the S transformation. So this is the S transformation of a character. By no means it is clear that this can be written as an expression in terms of characters. This computation tells you, oh, it can be written as an integral over characters. Right? This computation tells you I do this funny transformation of variables, and if I think about it correctly, meaning in terms of a Gaussian integral, I immediately get it as an integral over ordinary good characters and the good variables. And then
why is this interesting?
This is interesting. So this is this is a natural analog of a finite dimensional vector valued modular form. I here have a vector valued modular form, but not over a vector space of countable dimension, but a vector space labeled by really basis labeled by real numbers. This is interesting because of this computation here. All right, I use then this S. I illustrated. So I get something that you should call a vector valued modular form on the space of characters, and the S transformation can be used to define a Valinde product, and the resulting Valinde product coincides with the fusion product of this morning. So, and this is interesting because it illustrates something that that is not a coincidence. Right? If it were a coincidence, I wouldn't present that.
So is it fair to say it's very difficult at the moment to see why it's interesting? I mean, to me, this Valinde product, as you've written it, is an extremely complicated way of writing something that you explained before was extremely simple.
Yeah, I think I must say I'm surprised because I find this very interesting, and I find it really nice that I get the very same numbers in two extremely different looking ways. Right? And
this is some extremely obscure way of writing the fact that Fourier transform has some property. I mean,
sure, that you can also view that that way. The point is, I computed, so I illustrated that what was a complete VOA problem, namely these fusion rules of Fock modules, right? And nothing with characters, nothing with analytic properties of these characters. And I've shown you that, yeah, if you can do this, you get that same type of product, but now on the space of characters. Okay. I simply computed the following statement. I have the product of, let me write it down, and I have this Valinde fusion product, and I have computed that is the same as the, and here I write fusion for VOA tensor for the VOA product. It's the same that I get on the VOA level. This is what I have computed, and this is what I wanted to compute.
But I needed to do the computation over there.
Yeah. I mean, you need to know. I needed to compute the S to be able to compute this. I wanted to compute this one, so I have to know what I have to plug in for this. But I take this kernel function that I get from the modular S transformation.
I agree, but the fact that it somehow implements the S, this is new stuff. And what is the meaning of that? Maybe we'll be revealed tomorrow.
Yeah.